Well, good afternoon, morning, or evening. Welcome to the 2021 Josiah Willard Gibbs Lecture, which was established by AMS Council in 1923 to showcase to the public the contributions of mathematics and its applications. It's a real great honor and pleasure to introduce this year's speaker. Following her presentation, I will be looking for questions from the audience in the Q&A. So please use the Q&A for your questions to the speaker and the chat for any other questions regarding technical assistance, comments, or just to say hello to one another. Lenka Zdeborová is a professor of physics and computer science in École Polytechnique Fédérale de Lausanne, where she teaches and leads the statistical physics of computation laboratory. She received a PhD in physics in 2008 from Université Paris Sud and from Charles University in Prague. After 2 years at the Los Alamos National Laboratory as the director's postdoctoral fellow, she was a researcher at CNRS working in the Institute of Theoretical Physics in France. Zdeborová has been awarded several prizes for her work. In 2014, the CNRS Bronze Medal. In 2016, the Philippe Meyer Prize in Theoretical Physics. And in 2018, the Irène Joliot-Curie Prize. Her research explores the applications of concepts from statistical physics, such as advanced mean field methods, replica methods, and related message passing algorithms, to problems in machine learning, signal processing, inference optimization. I thank her for accepting the invitation to give this lecture, and we are all looking forward to learning what physics teaches us about computation in high dimensions. Please welcome Lenka Zdeborová.
Thank you so much, Jill. What a pleasure to be here, even though it's far away from most of you. So I would like to start my lecture with thanking my collaborators. I decided to list all of them because collaboration and discussion is something that I really like a lot in research and that I miss a lot in these times of social distancing. So for the next 50 minutes or so, I would like you to think with me about the following question. What are the problems that we can solve using a computer? So if you were an undergraduate student and were interested in this question, you probably enroll in the lecture of computational complexity theory that stands on these two works that came out almost exactly 50 years ago, half a century ago, by Cook and Levin, introducing the concept of NP completeness and proving that a certain problem is NP complete. So that is, the standard notion of hardness. But that lecture that you would attend would actually not explain the following empirical observation that we are observing in practice every day these days, that these NP hard problems are actually being solved in practice every day. So that might not be the most practically relevant notion of hardness. And an excellent example of this statement is the very field of learning with neural networks, the deep learning and artificial intelligence about which we are hearing so much these days. Learning with neural networks is indeed an NP-complete problem for even very simple neural networks, as stated in this work from '89. But we also know that today it's fair to say that artificial intelligence is the fourth industrial revolution, and we see amazing practical successes such as winning in the game of Go and being able to fold proteins and being able to translate from languages to languages automatically. Yet, we do not have a theory that explains what makes these problems solvable in a computational tractable way. The traditional worst-case computational complexity theory is not covering that. So we need to think about a theory of algorithmic hardness that would capture what's happening for natural distributions. And that is what I want to discuss with you in this lecture. I want to start with an example of two works that that were very influential for the line, for what I want to be telling you today. And that's the two where the really hard problems are, and hard and easy distributions of such problems. These two works introduced the problem of random satisfiability. So Boolean satisfiability is a problem where you take variables xi, true and false, and then you create clauses of logical ORs, and the clauses are connected with logical ANDs. And the random k satisfiability problem has k of these variables in each of the clauses. These variables are picked among n variables, and one has m clauses. And the variables are picked at random to each of the clauses and negated with probability half. And if you create the problem this way, then the two papers that I cited coined and observed the following intriguing phenomenon. So you can ask, what is the probability that thus created formula actually has a satisfying assignment of those variable x that is satisfiable. You can plot that probability as a function of the ratio between the number of clauses and the number of variables for different sizes of the system, for different number of variables from which you are picking. And you observe that as you are making the system larger and larger, this curve drops from 1 to 0 in a sharper and sharper manner. And if together with that, you measure the median time that a typical algorithm that you can use to solve such a problem takes, you observe that the running time of this algorithm goes sharply up around where the curve drops. So this had led these two works to the following conjecture that A, there is a sharp threshold in this parameter alpha, such that below it, if the system was infinitely large, the probability would be 1, and above it, the probability of satisfiability would be 0, and the hard instances lie close to this threshold. And back then in the 80s, when these works came up, nobody really had a clue how to explain or how to understand such an observation. Perhaps until a few years later, when works by physicists came into the game. And these are really two papers that, especially this first one, that made me personally come to the field, because when I read it, I found it so fascinating that's what made me decided that this is the field that I want to study. So in these works, not only they were able to compute the value of the satisfiability threshold, which is this value here is 4k equals 3, but they also suggested or hypothesized the reason for the algorithmic hardness in this problem is related to what in physics we call phase transitions. And since then, this field led to beautiful interplay between these physics works and mathematics. So one work that came a decade later was actually proving rigorously that this conjecture that in the physics work was done not just heuristically without a proof. So this is a field where really the predictions from theoretical physics and the rigorous mathematics interplay in a very collaborative and incredible way. So, and this paper, it's not very often that you see in mathematics that papers are directly relying heavily on insights from statistical physics. And these heuristics guide the proof of the limiting density, at least for a very large K in this case. And this paper was quite well appreciated in the community. So to sum up this very introductory part of the talk, let me, in few historical items, summarize what I just said. So in the late 70s and 80s, actually people studied different ensembles of random case satisfiability problem that was on average algorithmically easy. And they actually thought that maybe it's hard to find the hard instances. Then the two works that I started with showed that the hard instances can be found next to the threshold. Then the physics works that I showed you hypothesized that it is a certain glassy nature of the problem that makes the problem hard. Then during actually my PhD thesis, we made this more precise and conjectured that it's a solutions of a certain type called frozen that are hard to find. But then later on, we actually realized that the known algorithms stop before the other solutions cease to exist. So in conclusion, where we are today is we still do not understand precisely what is the range of this parameter alpha, the ratio between the number of clauses and the number of variables, where this random case satisfiability problem is hard. So that illustrates to you that even in such a case, how hard this question actually is to understand the hardness of some natural distributions of problems. So what this lecture will be about is here I give the book for which Gibbs is very much known. I will show you how the statistical mechanics that Gibbs developed, what it teaches us about the computational problems. And I will show it to you on a class of problems where we actually understand more precisely what causes the algorithmic hardness, or at least what is the range of parameters in which exactly it appears. Not rigorously yet, but at least on the physics level, we understand it much better. And this class, I call it the high dimensional Bayes optimal inference. So to tell you an example of a problem that belongs to this class, let me start with a little card game. So imagine that you have a room of people, 15 people in this case, and you have a deck of cards that contain values. Each card is either +1 or -1. And now I deal the cards to the people. So everybody gets one card with one of the values. They see their card, they see each other's card, but I don't see which card they got. The game for me will be to gather some information about which cards they have that I will define in the next slide, and then use whatever computational power I have to actually estimate which cards they have. So the information that I will gather is the following. I will go to every pair of people, so these two in this case, and ask them the following thing. I will ask every pair to generate a random number W that will be just a Gaussian variable with zero mean and variance delta star. And then to add to this random number 1/square root of n, where n is the number of people, if their cards were the same. So again, they see each other's cards, I don't see their cards, and subtract 1/square root of n if the cards were different. And then I collect these numbers, random number plus or minus 1/square root of n if the cards were the same or different, from every pair in a matrix that I will call Yij. And my goal will be to recover the card values from the knowledge of this matrix, or at least to recover them up to the sign flip. I don't have any information to say who has which sign, but can I split the people into two groups so that one group has majoritarily one card and the other group has majoritarily the other one? So that's what I aim for. Now the question is, what is the minimal achievable error that I can do in this task? So this is what I will go after. And a variant of this question is, what is the minimal but computationally efficiently achievable estimation error on the values of the cards X star? So both these questions I will be interested in. So how to solve this problem? This is a probabilistic problem. So we first formalize it, write things mathematically. I introduce X star, Xi star, the values of the cards for a person I. And then the observation that I actually have the matrix Y can be written this way, where the W, as before, is the Gaussian with zero mean and variance delta star. And then I call X without a star hypothetic values of cards, and I can write the Bayes theorem and write that the probability that the whole vector of cards is X, given what I observe the matrix Y, is written as a probability distribution stated here. Now, I recall my classes of statistical inference, and the way we would typically estimate what is the ground truth value X star would be by maximum likelihood, or very similarly maximum a posteriori estimator, that is maximizing the probability of observing a vector X given the observations Y. But we will not be focusing on the map estimator here, because we will be interested in the system size n being very large. And in the way I define the problem, in that case, this probability would be exponentially small in n. So that's perhaps a less relevant notion of optimality. We will rather focus on a notion of, we will want to minimize a pointwise error, sum over all the people in the room of some distance between what I estimate and what is the ground truth value of the cards xi star, where this distance can be Kronecker delta function between the two, or square difference. This can be different functions. Now, in order to minimize this notion of error, what I need to do, I need to compute the marginals of this probability distributions defined this way. And an estimator based on these marginals, we will call it the Bayes optimal estimator. Now, this is all well known. The trouble with this is that it's both mathematically and computationally difficult to deal with probability distributions over vectors that are high dimensional when the n will go to infinity. So how do we analyze the performance of this card game that I introduced? So we will simply map it to a spin glass by renaming the y j and the x s. Now you will tell me, well, this is silly. First of all, renaming doesn't solve anything. And second of all, I don't even know what's a spin glass. So you do know what's a spin glass, because the game that I just introduced to you, that's exactly what a spin glass is. And renaming things is maybe not that silly, because if you do that, you can actually formulate the very same problem in the very language that Gibbs himself developed, in the language of statistical physics, where instead of calling this the posterior distribution, you call it the Boltzmann or the Gibbs distribution, depending in which part of the world you studied. And it's written in terms of the normalizing factor, which is the partition function, and the exponent in the exponential is the Hamiltonian. And you were right that renaming things doesn't solve anything. But if you actually look into the literature on statistical physics of disordered systems, you realize that exactly this same type of problem has been studied more than 40 years ago and is known under the name of Sherrington-Kirkpatrick model, where the J or the Y, the matrix that you observed, is the disordered. This Sherrington-Kirkpatrick model has a slightly different disorder. So if you dig a little bit more into the literature, you realize that back then, 40 years ago, the physics literature solved exactly that problem in the limit of large systems, which in statistical physics is very natural, because the n corresponds to the number of molecules, and that's typically as large as the Avogadro number. So that's the very regime for which statistical mechanics was developed. The method to solve this problem is called the replica method. And in order to dig it from the literature, you would need to do a little transformation of your variables, which for the purpose here will not be important. But then you can take well-known textbooks and articles in there where they print a phase diagram, which is exactly solving this problem. So that's if you want to dig into the 40 years old literature. But let me simplify it for you and state it in a way that is a bit more current. And that is also relying on the interplay between this part of statistical physics and mathematics that I was already mentioning. Especially in the past decade, there has been development in establishing these physics methods rigorously, so that the solution to the very card game that I introduced to you can be now stated as a theorem that has been proven in this line of work. And the theorem says that the key quantity that we call free entropy, which is the logarithm of the normalization of the posterior probability distribution divided by the system size, as the system size grows, concentrates around the maximum of a function of a single scalar variable m. M is just a real number here. And this is a simple function in the sense that m is a scalar function. This expectation here is over scalar variables. One of them is Gaussian, the other one is distributed in the same way as the cards in your deck were distributed. So this is a simple expression that you can easily evaluate and compute its maximum, as contrary to this expression where x was n-dimensional vector and was large. And this is pretty much something that is in general difficult to deal with. And if you don't come from statistical mechanics, you don't see immediately why this free entropy is the quantity of interest. So it's maybe the theorem 2 that will make it clear, is that the maximizer of this free entropy function is also directly giving you the optimal mean square error that is achievable by any algorithm, whether computationally efficient or exponentially costly in the size of the system. So if you want things a bit more graphically, you can forget the previous slide and just trust me that the formula on the previous slides leads to the following picture. That is the accuracy or the overlap with the ground truth that you can reach as a function of the variance of the noise of the number W that you were generating. So if the noise is small, you will guess everybody right. So your accuracy is 1. And if the noise is large, well, you will not guess anybody correctly. You will just do as bad as random guessing, and that corresponds to the value 0 here. And what's striking is that there is a sharp drop of this curve to 0 at delta exactly 1. And that's a phase transition of the very same type that you might have learned about at high school when you were talking about magnetism. The type of phase transition that happens in magnets at the Curie temperature, which is quite high, over 1000 Kelvin, is exactly the same type of a phase transition that we are observing here in this computational card game that I'm talking to you about, where the phase where the accuracy is good corresponds to the ferromagnet, and the phase where the accuracy is 0 corresponds to the paramagnet. But going back to the question about what is the minimal achievable estimation error on X, there was this important part of it that was saying computationally efficiently. And so far, I put that green computationally efficiently under the carpet. So let's talk about it. So that brings us to the connection between the statistical physics approach and a class of algorithms that are called message passing algorithms, of which a belief propagation is the main example. This is an algorithm that, as every important concept in science, was independently discovered in at least 3 different subfields of science: in error correcting codes, in Bayesian inference, and in physics. But at first, people didn't know about each other and the connection. That became apparent only about 20 years ago. So the algorithm is called message passing because it is really in a sense sending messages between the people. These nodes here would be the people over the edges, which are the pairs that you queried when I was introducing the card game. So these messages are concatenating information from the neighbors that captures what's going on in the posterior measure. So I won't be going into details here, but there are versions of this belief propagation called approximate message passing, which is equivalent to the belief propagation for the problem we are talking about in the limit of large systems, but simpler. So all that has literature about it, but the bottom line here is that there are key theorems telling us that as the system size is large, the performance of these algorithms, the approximate message passing algorithm, follows gradient ascent of this free entropy function that I showed you a few slides ago, the very same function. And this property is called state evolution, and it also tells you that looking back at this function of one variable, you can understand the performance of this algorithm. And going back to the picture that you've already seen, if you apply the state evolution to it, you realize the result is that the optimal performance is achieved by the approximate message passing algorithm in this case for all values of delta. So no average computational hardness here. So if that was always the case, the talk would be maybe a little boring. But here in nature, the phase transition in ferromagnets is called second order phase transition according to the classification that is traditional to physics. But we also have first order phase transitions, such as the one when water is evaporating or water is freezing. And those really are the more interesting ones, the leviathans of the statistical inference. So in order to get a first order phase transition in our card game, because I won't be changing the system now that you know this one, I need to adjust it just a little bit. I need to put zeros into my deck of cards. Previously, I only had plus ones or minus ones. And now I will get a deck of cards where a good fraction of the cards is zero. It's this delta function of zero. This actually is a practically relevant problem in data science called Sparse PCA, but for our purpose, we will stick to the card game. And if you apply the very same theorem one from previous slides, the expression was generic enough to account for a generic distribution of the cards in the deck. And you evaluate the maxima of the free entropy function as the blue curves and the minima as the red curves, you get the accuracy as a function of the noise. You get this curve here where for certain values of the noise, actually you have several solutions. And now when we put together what was the statement about the optimal accuracy and what was the statement about the performance of the algorithm, we can actually split this phase diagram into three regions. The green one, which is an accuracy that the approximate message passing algorithm is able to reach. And then the purple one, where no algorithm, whether exponentially costly or not, is not able to get such an accuracy because simply the noise is too big. This is not possible statistically or information theoretically. And then the most interesting, the blue region, where if you had an exponentially costly algorithm, you would be able to get an accuracy in this blue region, but the approximate message passing algorithm will not give it to you. Now that's one algorithm. You can say maybe there are better algorithms. So this is where it gets striking. There is a hard phase conjecture that in the problem we are talking about states that actually no polynomial algorithm will work in this hard phase. That is, approximate message passing algorithm in this case is optimal of the polynomial algorithms. So saying something like that, if you know about computation complexity theory, you realize this is a very bold conjecture. And nevertheless, it's physically sensible, decade of works or attempts of breaking that conjecture and failing to break that conjecture. And of course, mathematically, this is widely open. We don't know how to prove that no other polynomial algorithm, will be able to reach accuracy in this hard phase. So now to bring you a little bit of an intuition of what is the origin of this hard phase in the computational problem, let me show you a physical system that is what it is for exactly the same reasons, and that is diamond. So unless you heard it before, you probably haven't seen coming a diamond here. So diamond is actually a metastable phase of the carbon at normal pressure, normal temperature. If you turned diamond into graphite at normal pressure and normal temperature, it would release heat, meaning that it would be happier as graphite. It would be energetically favorable for diamonds to be graphite and not diamond. Yet we are not really worried that our diamonds will turn into graphite spontaneously at normal pressure and normal temperature, because the metastability in diamond is very, very long living. Now there is a subtle difference between diamond that lives in a three-dimensional Euclidean space and the algorithms that live in high-dimensional space, and those are really stuck for exponential time. Another example of this metastability is supercooled water. So you can put water into freezer and do it carefully. Now the video was probably too slow over the Zoom to really see. So this water was cooled below the freezing temperature, yet it remained liquid. And when you hit the floor with the bottle, you introduce an impurity inside the water that will induce a nucleation of a crystal, and the crystal will grow with a pretty good speed in the bottle. And you probably see the video with too few frames to see the crystal grow. So a summary about how the physical states of matter, of liquid, supercooled liquid, and ice correspond to the computational impossible, computational hard, and computationally easy regime in the phase diagram of the card game that we introduced this on this slide. So now you may ask yourself, is this card game somehow a special case where this hard phase appears? So not at all. So this list is a list of other computational problems where exactly the same hard phase appears. And you may say it's long, but it's only papers from my own work. If I actually included works by other authors, it would have been much, much, much longer. So the computationally hard phases of exactly the same origin appear in very long list of inference problems. And if you want to learn more about those specifically, later this year, there will be a dedicated program in the Simons Institute of Theory of Computing about the computational complexity of statistical inference. If you read the first three lines, it's exactly about the topic I'm telling you about. So now that you know about the first order phase transitions and the computational hardness they induce, sorry, too fast. You can ask yourself a question, is it useful for something to know that the hardness is due to the presence of the first order phase transition? Can I get a better algorithm from that, for instance? So I would not be teasing you with the question if the answer was no. So the example where you can get a better algorithm, a better system by this understanding is one of the works that I listed, the one on compressed sensing. So now I need to go away from the card game that we played and introduce you to a new problem, that is the compressed sensing. The compressed sensing is a beautiful idea of imaging. So when you're measuring an image with a camera, for instance, you classically take every pixel one by one and store them. But then once you store the picture, then you can compress it. You can use a compression algorithm in your computer and compress it to much smaller size picture. And the idea of compressed sensing is, couldn't I skip taking all the pixel one by one? Couldn't I take a number of measurements that directly corresponds to the size of the compressed picture? And you indeed can, in a certain sense, and that's exactly the idea of compressed sensing that was introduced some 15 years ago and became quite popular since, as you can see by the number of follow-up works. So now I just said it in words, but this is something that you can formalize mathematically, because taking a measurement of a signal X is in many cases just multiplication by a matrix F that corresponds to what your measurement apparatus is doing. And the product of this matrix and the vector is the measurement that you're taking. So the question here is that if you want to measure an X vector that is large, but many of its elements are actually zero because you could compress it, can you measure fewer elements of Y and still be able to reconstruct the vector X? So again, I'm not going to details, but you can apply the very same replica theory and this very analogous type of proofs to this problem and end up again with a phase diagram where you split the region of parameters, which in this case, the rho is the fraction of non-zeros you had in the signal, which corresponds to the compression ratio by how much you were able to compress that signal. And the axis here, the alpha, is the ratio between the number of measurements you took and the overall size of the signal. And again, it splits into regions, an easy one, the blue and green here, the hard one and the impossible one, with exactly the same physical origin of the hard region. This line here is again a first order phase transition. But now there is the important difference between this problem and the card game is that here we have the measurement matrix F that is not given to us by the processors. That is something that we can design. The camera, the measurement apparatus, we can design it. So we have a freedom to choose this matrix F. And if we have this freedom, then going back to this concept of metastability that is making computational problems hard, but at the same time, if we embed the system into, in this case, three-dimensional space, but it could be any finite dimensional space, 1, 2, 10, and we introduce an impurity that induces denucleation, then the ice, which in this case was the good accuracy solution that we desire, will appear. And this is described in physics as the concept of nucleation. And nucleation always happens when the dimension of the space into which the system is embedded is finite. And if that is the case, then the surface of a drop gets eventually, for large enough drop, smaller than the volume of the drop. And thanks to that, if the impurity is large enough, bigger than some critical nucleus L star, then the surface of the favorable case, the volume of the favorable case will start growing. And this is a physical concept of nucleation that you have seen on the previous slide with the water freezing in the bottle, that we can actually, by design, impose to the compressed sensing problem by designing the measurement matrix in a particular way. So it will be this band diagonal matrix where the band serves as a one-dimensional structure that is effectively embedding this high-dimensional problem into one dimension. And the first element here is longer, that serves as the impurity that will induce this nucleation. And if we do that, we indeed completely destroy this hard phase in the phase diagram. And thanks to that, we make the compressed sensing computationally tractable down to the information theoretic limit and destroy this hard region. So this is where it has been done and where it has been proven mathematically that that's actually the case. And I should, to be fair, I should say that this concept is called spatial coupling. It has not been for the first time introduced for the compressed sensing, but for error correcting codes. And before the previous works that I was telling you about in these works. And this concept of spatial coupling is applicable to all inference problems where the interaction graph or the matrix F can be designed. And here, sorry, here the video here is showing you, it was running, no, it is not running anymore. Sorry, trying to go back to it. Is showing you together the nucleation of the ice in the bottle, how the error correcting code is correcting the picture, and the type of wavefront that propagates in the reconstruction of the picture. Another thing that is very, very interesting about this spatial coupling is that not only it can be used to design better compressed sensing protocols, but it can be used as a proof technique. And again, that's something quite remarkable that has been suggested in the error correcting codes literature. And now this paper is going back to our card game, because I only cited a couple of works to prove the theorem 1 and 2 that I was giving to you. I didn't tell you about the proofs. But in the first proof that we provided, the concept of spatial coupling was one of the 3 enabling factors. We actually, in a part of the proof, mapped to the spatially coupled system that allowed us to prove something that otherwise we couldn't, and then we mapped back. So these insights from statistical physics are also leading to new proof techniques. And as I am kind of slowly going towards the end of the lecture, I want just very briefly to come back to this slide that I gave you in my motivation about what is the kind of currently active area where we don't know where the computational efficiency actually comes from, and that's the deep learning. So what is what I'm telling you giving us some perspective on the theory of deep learning? So I want to make 2 points here. So one point is that the hard phase that I'm telling you about is also present in learning with neural networks. And one example where it can be coined out very precisely is the example of the committee machine, which is a simple neural network with its input data and one hidden layer of k hidden units and an output y, with the input dimension being p, and that goes to infinity. The number of samples is n, and that goes to infinity. But the ratio between them is some alpha that is fixed. And in this limit, for input data that are ID Gaussians and labels that are generated by a teacher neural network of the same architecture. So for a neural network of this type in these works, we could actually analyze again when exactly it is learnable and when it is learnable computationally efficiently. And in the case of k being rather large, but after the n and p when sent to infinity, we again get a phase diagram with, in this case, yellow phase that is the hard phase between what we conjecture is the best algorithm for this problem is achieving, and what would be achievable if we actually had exponential computational resources. So the hard phase does appear in learning with neural networks when hidden variables are present. And also, learning is not done usually with message passing algorithms or approximate message passing algorithms, but with gradient descent. So that's a different type of algorithms. But we also show that also gradient descent based algorithms are influenced by the presence of the hard phase when it is there. And when the hard phase is there, then it actually causes hurdles also to the gradient descent based algorithms. As we showed in a work on, again, I'm not defining what this precise model is, please go to the references if you're interested. But again, a phase diagram for a model called the 2+3 spiked matrix tensor model, where the hard phase exists for the approximate message passing algorithm. And the fact that it's there causes the gradient descent not to be working in an even larger region than the approximate message passing algorithm. So these are just two small pieces into the puzzle that so far is a widely open question. That is, how do we really combine the three key elements of machine learning, which is the architecture of the neural network, the type of algorithm that we are using to train it, and the very structure of the data on which we want to learn something. That's, this third ring, the structured data, is often somehow omitted from the considerations in the theoretical literature, which is crucially not correct in the sense, if we consider worst case data, then we know that the problem is algorithmically hard. So there is something in the structure of the data that makes it tractable. But this is somehow among the challenges on which my group and many other people in the world are working. And going back to the fact that this is a Gibbs lecture, I would really like to think that along the lines of Gibbs, who took thermodynamics, which in his times was very practical but very empirical field, and formalized it, established its foundations under the name of statistical mechanics in a way where suddenly mysterious equations and laws became very natural. So I would like to end this lecture by hoping with you that we will soon reach something like that for the theory of average algorithmic complexity and the theory of learning and deep learning. And with this, I will go to my conclusion slide. I hope I showed you in this lecture that many problems studied in mathematics, statistics, signal processing, and machine learning can be formulated as physics models of disordered systems. That, as in physics, we find phase transitions in these systems, and notably the first order phase transitions imply a sharply defined algorithmically hard region in the inference problems that stands as a very big mathematical open question to actually show that it is algorithmically hard, but so far resists attempts to show that it is not hard, that some algorithms can work in the hard region. It doesn't seem so. And this statistical physics analysis leads to new insights and new algorithms and new proof techniques. And with this, I think we can open for questions if there are some in the audience.
Thank you, Lenka, for that terrific talk. I would like to open it up for questions. I think that we have one that we should start with, which is someone in the audience has asked, if we want to learn more about this, what resources or papers would you recommend?
So there are many. I should. Yes, please send me an email. I will send you a list. So the kind of time consuming one is, I cited this program in the Simons Institute in Berkeley. If you ever had the chance to participate in that, I'm sure you would learn a lot about these computational hard phases. There is a review that I wrote in 2016 that is called Statistical Mechanics of Inference, Thresholds and Algorithms. So that review summarizes some of these findings. If you want to learn more about the methods and the algorithms, there is a wonderful textbook from 2009 by Mézard and Montanari on the field. And there will be many more references if you're interested in more recent things on the machine learning side, for instance. There I would send you an email if you send me the question by email.
Yeah, thank you for welcoming emails to find out more about this subject. I'm sure that some people would love to see the slide on references again. And let me go to the Q&A to find another question. So here's one. So one of our audience members asks, what is the advantage of using physics models of disordered systems over purely math models?
So I would say the advantage is the time. Since in physics we study these high-dimensional probability distributions for over 100 years, we are a bit ahead, and some of the methods that I was citing here were developed in the 70s, where mathematically nobody has had a clue how to prove these theorems. I mean, there were attempts, and people studied in mathematical physics these spin glasses from very early on, but they were known as something very hard to approach. So the big mathematical developments were really happening later from kind of the physics theories. So in my, it's not that there is something fundamentally more in physics. I really think is the many decades ahead of studying high dimensional statistics, calling it differently, that made kind of physics ahead in these topics.
So maybe very early on, this is relevant to this question. You showed a slide in which the physicists computed this threshold parameter alpha in phase transitions, 4.26, etc. Is there some significance of that number, or something else that one can say about that threshold number? Any further understanding?
So there is a closed formula, which is an equation that fits one line, implicit equation of which this number is a solution. So as far as we know, there is no simpler way to express it. The formula is very explicit. As I said, I could write it on half slide, but proving that that's the right formula for the phenomenon that we are describing, that is highly non-trivial, and that has only been achieved in that paper in 2016. So the formula was given 15 years before that by the physicists, and proving that that's the right formula for the problem took 15 more years. So that's the average time for this type of problems. Some of these, for instance, the solution of the Sherrington-Kirkpatrick model that I was mentioning, that is formally more complicated than the problems that I was presenting to you. It has been written in the physics literature back in '78, and it has been proven by Talagrand at the beginning of this century. So say more than 20 years after that. So that's kind of the average gap in this field. It's several decades. Maybe it's less these days. Who knows? If we are still ahead.
People are very intrigued by this translation of physics into algorithms, and are asking some questions about the things that might also be translated. For example, Is there in this translation, is there an analog of a critical point or associated scale invariance? Or if the impossible region is like liquids, is there an interesting fluid dynamics? So
yes, so the critical point, absolutely. So critical point is the point where, you know, the for instance, the transition from the impossible phase to the easy phase, from the paramagnet to the ferromagnet. In a sense, the fact that the algorithm, even in the original card game with the plus one and minus one, where I concluded that it's actually algorithmically easier, it's true. But if you go really close to the critical point, the algorithms will have running time that actually grows as you're approaching the critical point. So you do have the analog of this critical slowing down as we know it from physics. And with that, you have studies, you know, about other aspects of critical phenomena that then translates to the running time of the algorithm. So that, yes, about the dynamics of fluids, well, certainly, I mean, the whole, I talked about spin glasses. The spin glasses are these magnetic materials that in physics are actually maybe less interesting as materials, but structural glasses as the one you have in your windows and colloids and materials like that do have physics that derives from very similar type of theories as what I was describing to you. So yes, there are analogies pretty much everywhere between this type of physics and computation problems. Again, if you're interested in something specific, don't hesitate to ask me, but there are too many things to say for me to answer better than that.
thank you. So here's a question of my own. I was intrigued by, but maybe didn't quite see what everything you were trying to say about the connection between spatial coupling as a proof technique. So you probably explained that, but I'd love to hear a little bit more about it since we do have a couple of minutes.
So again, I didn't really explain that. There are several things to say about it. Maybe one of the things to say about it is that, okay, that was the first proof that we came out that took maybe close to 100 pages. And after we came with that, in the 2 years that followed, there were 3 or 4 papers simplifying that proof very, very drastically, not using the spatial coupling and making it about 5 pages. So if I would be actually presenting in a lecture the proof, I would probably not pick the one that uses the spatial coupling. Still, for me, it's an important one because that's the first one that kind of cracked the way we can enter, in a sense, mathematically into the hard regime. So the proof techniques that were there before were working for the version of these problems where this free entropy phi of m that I introduced has a unique maximizer. So if it has a unique maximizer, then coupling this fact together with the rigorous analysis of the algorithm and using some data processing inequalities actually led to the proof that the algorithm is reaching the optimal performance and the other bound was simpler. Now, when the hard phase exists, then the algorithm is not reaching the optimal performance. So that prevented that proof to go through. But if we introduce the spatial coupling, then as I said, the hard phase gets destroyed. So this way, the algorithm can reach the optimal performance and that previous proof technique gets to work. And now we just need to kind of glue it on the 2 ends and show that introducing the spatial coupling doesn't change the free energy in the limit in which we are interested in. And that's something that one has to work quite hard on, but that it's possible to do. So that's kind of how it entered in using pieces from the previous works and the link between the algorithm reaching the optimality.
Thank you for that. So I see that we're just about out of time. So I'd like to thank you once again on behalf of AMS for this amazing talk. And I wish you were able to hear a round of applause and read some of the wonderful compliments in the chat box. But thank you again, Lenka. It was just terrific.
Thank you.
Thank you so much, Jalen. Thank you for